what is the average height, and here height is just value of the function, for the bowl f of xy equals x squared plus y squared over the region x squared plus y squared less than 2x. And it says, hint, one of the following might be useful. And we have some options, and some of those look like reasonable numbers. Some of them look like weird numbers. But do we have an answer? A, B, C, D, or E? Was anybody working on that? I hope some people were. Do we have a guess? C. C is a pretty good guess. It was meant to be distracting. But it's not C. B? B is the answer. Now, how does this work? So the one that was useful was the last one, the integral of cosine to the fourth. And you have to understand a few things. You have to figure a few things out. First off, what is x squared plus y squared equals 2x? That's this circle centered at x equals 1, y equals 0. You can convert it into polar, r equals 2 cosine theta. You might say, well, why might polar be a good thing to do with this problem? Well, whenever you start seeing things like circles, that's a pretty good hint. And x squared plus y squared, in particular, if you see lots of x squared plus y squared showing up, circles. Now, one thing to keep in mind is, how do you compute averages? Now, well, it says it right here, but where is this coming from? So if you put back your Calc 1 hat, do you remember how to do averages from Calc 1? So it was the integral from a to b of f of x, but then there was something else. Right, 1 over b minus a. Now the question is, what is this 1 over b minus a doing? If you think about it for a second, what is b minus a? So you're going from a to b, you have your function, here's your f of x. So b minus a, that's the distance between a and b. But you can also think of this as b minus a. You can say, this is the same as, you still have this integral upstairs, and it's the integral from a to b of 1. So really what's happening is you're dividing by the size of your region. And in one-dimensional calculus, the size of your region is the length. In higher dimensional calculus, well, the size of your region, it could be an area if you're doing 2 integrals, or, spoiler alert, for today, it could be a volume if you're doing 3 integrals. So the punchline is you're integrating this function over your region, then you divide by integrating 1 over your region. But the nice thing about integrating by 1 is that's your area. And it's easy to find areas of circles because we learned that a long, long time ago. So you're dividing by pi. So then you just work it through. You set up your integral going from negative pi halves to positive pi halves. I didn't put my negative sign there, or it's very tiny. Yeah, and that didn't help. There we go. That looks like a negative sign now. From negative pi halves to positive pi halves for theta, 0 to cosine theta. As a reminder, when you're setting up your region, you always come from your origin. So you're going from your origin out to the curve. So where does r go from? It goes from the origin 0 out to the curve 2 cosine theta. And anyways, you end up having to deal with the integral of cosine to the fourth, but that's given. Life is good. 3/2 is the answer. All right, any questions? So if you see a problem like this somewhere else, you'd be like, yes, I'm ready. I can do this one, right? All right, good. Easy, good. I was worried. I was getting nervous. So, thought for today, probably a nice thought after an exam. The road to wisdom, well, it's plain and simple to express. Err and err and err again. but less and less and less. So you're going to make mistakes. And when you get your exam back, I hope you look at your mistakes and you say, okay, what mistakes did I make? It's not about being perfect the first time. It's about learning to become better. So we're learning from our mistakes. And you can't learn from your mistakes if you don't look at them. And I know it's uncomfortable. It's incredibly uncomfortable to look at your mistakes and say, I have no idea why I did that. I feel like such a silly goose. I think that's what the kids say these days. I'm a silly goose. But look at your mistakes, learn from them, and then say, okay, I'll make fewer of those mistakes in the future. I'd like to say, you'll never make that mistake again, but I still make some mistakes. The key is to make less and less and less. All right. Good. By the way, you may have recognized this name. This is the second time we pulled the quote from Pete Hine. He has another lovely poem about losing a glove. Nothing feels as bad as losing a glove, except for losing the glove, throwing it away, and then finding the glove you lost. So, and that has a very interesting history. You should look it up. All right. So, goal for today, we're going to keep moving up in dimensions. So we've been doing two-dimensional integrals. We said, we can do two-dimensional integrals in Cartesian coordinates last time. We talked about two-dimensional integrals in polar coordinates. But it's really two dimensions. Whether we use Cartesian coordinates or polar coordinates, it's not changing the underlying idea. It's about finding the total over some region. We choose different coordinate systems to help make things easier, ideally to help make things easier. And so we say, okay, well, but what happens in three dimensions? So we're going up to triple integrals. Now, the underlying philosophy is the same, which is to say, well, what can we handle? We can handle small things. And so we might say we can take our solid and break it up into tiny little cubes. So here's a little piece of our solid. And when we look at it, we say it's very easy to understand what's happening. There's a small change in the y direction. There's a small change in the x direction. There's a small change in the z direction. And so that our volume here, this is our delta x, delta y, delta z. And we say, all right, chop things up into cubes. And there are other ways to chop things up. And that's what we're going to be talking about next week. Spoiler alert, come next week. It's going to be a lot of fun. And then you say, okay, so what do you do? So now that we've chopped things up, the nice thing is if we're trying to find a function, we can say, well, in a little piece, we can treat functions like constants. So our total, well, it's approximately the sum. And there's three sums because we have to move in three directions. F, xi, yj, zk. We have our three sums here. And delta v. Well, we denote this by saying in the limit as our pieces get small, this is the integral over our solid of f of x, y, z, dv. Now, so that's the theory. Break things up into small pieces, add the pieces up, life is good. What's our practice? How do we actually do this? Well, we channel what we did in Calc, not Calc 2, Dimension 2. What did we do in Dimension 2? We did it one variable at a time. Just take it one variable at a time, right? Like the song. So we sliced and we diced. And what are we going to do now? We're going to do the same thing. We're going to slice and dice. So we say, okay, let's take our solid and we'll slice a little piece of it out. Why not? All right. And so we have now our slice. And the nice thing is we say, well, how do we handle our slice? Now, because it's a big slice, the function isn't acting like a constant, but that's okay. We can say, well, what's happening? Well, our total is approximately, of course, the sum over all our slices, the value of the slice. Well, if we think about that, that's really saying it's an integral with respect to z, because in this case we're slicing in the z direction, and the value of the slice at z and dz. Well, the bounds depend on the problem, and they say, but the nice thing is this slice is acting like a two-dimensional shape. And since it's acting like a two-dimensional shape, we apply our two-dimensional tools. So we get an integral from the outer layer, an integral middle layer, integral from the next layer, and f of x, y, z, and there's some ordering dx, dy, dz. Now, the bounds, of course, depend on the shape, and we're going to spend, essentially the big thing about today is setting up the bounds. But that's the idea. That's our philosophy. So in practice, actually computing the integral, same things that we've done before. Just work from the inside out, one step at a time. So most of our effort is going to be talking about setting things up, but we should do at least one integral through the end. Any questions about the basic idea? Okay. All right, well, let's do an integral. Find the integral of over a region S. So we're using S for solid. Sine of x plus y plus z dv, where S looks like what? Well, it says x goes between 0 and pi halves, y goes between 0 and pi thirds, and z goes between 0 and pi over 6. All right, well, what kind of shape is this? Now you might be, I'm hearing sphere, but that's because we see pies. But suppose they weren't pies. I said x goes from 0 to 2, y goes 0 to 4, z goes 0 to 5. What do you see? It's kind of like a cube, right? Essentially, it's like a box. Like cube, there's sort of an implication that all directions have the same size. But here, well, they have different sizes. So, but it's a box. Okay, so when your bounds are constant, these are our happy times, because we like boxes when we're doing Cartesian coordinates. It makes life easy. So we say x goes up to pi over 2. Y goes 0 to pi over 3. So if I'm just looking at x and y, I have that portion. And then z goes to pi over 6. And so, I just aimed that, but all right, there we go. We have our box. Now, the nice thing about setting up integrals for boxes is they're very easy to set up. So, we're going to set up our integral. And our function, this is our function f, sine of x plus y plus z. And now we have to choose an order of integration, because you can. There are different orders of integration. Just as you could do dy dx or dx dy, here you've got a whole smorgasbord of choices. So we just pick an ordering. All right. dz, dy, dx. Why not? Why not? Okay, so how do we set our bounds up? Well, for rectangles, for boxes, it's not too much of a surprise. Let's talk about z. So in the z direction, so that's this direction, up and down, where do we go between? Yeah, 0 to pi over 6. All right, in the y direction, Where are we going between? 0 to pi over 3. And in the x direction, where do we go between? 0 to pi over 2. Okay. So no big surprises. And now we start working it out. If this was an integral where it was like x and y and z were products, and there's a lot of multiplication and we could pull it apart, we could separate. Unfortunately, this is not that integral. So one layer at a time, and just be patient. I haven't done this problem yet. So, we'll have fun. And if we get stuck, I put some reference up here. Okay, so first off, what's the integral of sine of x plus y plus z with respect to z? Positive cosine or negative cosine? Negative. Okay. So 0 to pi over 2, 0 to pi over 3, negative cosine x plus y plus z. Evaluate from z equals 0 to z equals pi over 6. And then we have dy dx. Okay, so that's integral 0 to pi over 2, integral 0 to pi over 3. Plug in z equals pi over 6, so minus cosine of x plus y plus pi over 6. Subtract, plug in 0. So minus and minus makes a plus, cosine x plus y. All right, so there's our first layer. And then we're going to integrate dy dx. Okay. Well, so we integrate. What's the integral of negative cosine of x plus y plus pi over 6? Negative sine of x plus y plus pi over 6. What's the integral of cosine x plus y with respect to y? Positive sine of x plus y. And then we're going to evaluate from y equals 0 to y equals pi over 3. And after we do that, we'll integrate with respect to x. Okay, so we'll start by plugging in pi over 3. All right, so this is equal to, we still have our outer layer, we haven't integrated it yet, so keep going. A lot of these have to pay attention. What have you done, what haven't you done? We haven't done our last integral, right now we're doing evaluation. Pi over 3 plus pi over 6, what does that become? Pi over 2. So we have minus sine of x plus pi over 2 plus sine x plus pi over 3. Okay, that's plug in the pi over 3. Subtract, plug in 0. Subtract minus sine x plus pi over 6. And then plus sine x. Okay, cool. dx. Now what? Now, we really can't combine anything because nothing combines. So, we get to integrate. Okay, integral of sine, negative cosine, and we'll just, I think we can all trust each other. So, integral of negative sine will become negative positive cosine, x plus pi over 2, minus cosine, x plus pi over 3. Minus minus makes a plus, then we integrate, so we end up with a minus again, cosine x plus pi over 6. Here we have a minus sine x, integral that is a positive cosine x. And then we're going to evaluate that from 0 to pi over 2. Okay, so we get cosine of pi over 2 plus pi over 2. Well, that's cosine pi. Pi over 2 plus pi over 3. Do we know that? So you can think that 3 pi over 6, 2 pi over 6 makes 5 pi over 6. Subtract cosine pi over 2 plus pi over 6. Two pi over 3. plus cosine pi over 2. That's plugging in the pi over 2. Subtract. Oh, this one is more fun than I thought. Okay. Cosine pi over 2 minus cosine of pi over 3 minus cosine pi over 6 plus cosine 0. Okay, good. Well, it'd be nice if that simplified. Does anything become simpler? Well, we have a bunch of cosines. The cosine pi's over 2's automatically go away. Cosine pi, negative 1. Cosine 5 pi over 6 is negative root 3 over 2, so minus minus makes plus root 3 over 2. Cosine 2 pi over 3 is minus a half. Minus minus makes plus a half. Then we have plus cosine pi over 3. So cosine pi over 3 is plus a half. Plus cosine pi over 6. Cosine pi over 6 plus square root of 3 over 2. And then minus cosine of 0. Cosine of 0 is 1. So we're left with root 3 over 2 plus root 3 over 2 is root 3. A half plus a half is 1. Minus 1, 0. There's still a minus 1 left. And so our answer is square root of 3 minus 1. And we're done. Isn't this fun? No. What? It's the same ideas, right? It's just work one layer at a time. Okay. I think that's our last do an integral for today. So, because now we get to the interesting parts. Which is, what is going on with these triple integrals? So you have to think about the notation here. When we talk about our bounds are important. Bounds are describing the shape. They're describing, in our case, the solid. The outer layer will tell us what's happening for our outer variable, right? So in this case, it's an x. It's going to go between a pair of numbers. When you move to the middle layer, in this case, y, we're going to go between two curves. And that was good enough for two-dimensional integrals. But now we're three-dimensional integrals. We're going to go to the inner layer, in this case, z. And now we're going between surfaces. So what we end up with is that we have that this is describing our region in the following way. So this says our region has the following description, namely that A is less than or equal to X, less than or equal to B. That's from the outer layer. Phi1 of X, less than or equal to Y, less than or equal to Phi2 of X. Our middle layer, and then this function psi, 1 of xy, less than or equal to z, less than or equal to psi 2 of xy. So this is the kind of description that we get from the bounds for our integrals. And if we want to put a solid into an integral, we have to find that description. So that's going to be our goal. How do we find that? And so we're going to practice that. Now, in addition to saying how do we describe it, there's another thing to keep in mind. There's many ways that we can slice and dice. So we talked about slicing our solid. So, if our solid has some sort of navy bean shape here, well, we talked about taking a slice in the z direction. But that's not the only way we could have taken a slice. We could also have sliced in, say, the y direction. And then we would have gone a slightly different shape. And we also could have sliced in the x direction. And that's a little bit harder to visualize. But the punchline here is we have lots of orderings. Since we have three variables there are 6 ways for us to describe our shape. Now, how do you pick it? Well, sometimes you don't have to pick it. It'll just say do the integral. Sometimes you should choose an ordering. And if you want to choose an ordering, choose one that makes things simple. In other words, try to choose an ordering so that the pieces involved are very simple. Or that it's not one where you have to break up into multiple parts, because that can happen as well. And also, remember, 0 is a friend. So if you can get 0 involved, do it. And, okay, I'm saying a lot of things. But I will say, if you don't have any other idea, this is sort of our default. dz, dy, dx. Now, it's not because this is better or worse. In some cases, it can definitely be worse. But the reason why this is a helpful default is because this is how we've been trained to think. We've been trained to think y is a function of x. We've been trained to think of z as a function of x and y. And so since that's what we're used to thinking about, that makes it very convenient for us. And so if we have nothing else to fall back on, that's a helpful tool. Okay. So let's try some things. Let's sketch the region for the integral. -2 to 2 for x. 0 to 4 minus x squared. This is with respect to the y. 0 to 4 minus z, and that's with respect to z, f of x, y, z. Now, we're not asking to find the integral because we can't. We don't know the function. But we can certainly sketch the region, or if you like, the solid that's associated with this integral. So, where do we begin? We start pairing things up. Okay, so let's work from the outside in terms of descriptions. What is the outermost layer telling us? So -2 is less than or equal to x, less than or equal to +2. We start at -2, we go to +2. That's the outer layer. And we know it's the x because that's the outer d symbol. What's the middle layer telling us? It's telling us about y. Where does y go between? 0 and 4 minus x squared. What's the inner layer telling us? It's telling us about z, and z goes 0, 4 minus z. I must have this copied down wrong, because that cannot be a 4 minus z. Oh dear, how did I get this wrong? Is it? Yes. Yeah, it can't be a z. Okay, I'm just thinking about the shape. What will make this most interesting? Y will make it the most interesting? Are you sure? Okay. We'll try y. And we'll see. I copied it down wrong. But, all right. Let's find out how this looks. This will be a fun exercise. Okay. Now, we need to sketch. This means we're going to get in touch with our inner artist. Oh, it's been a while. Okay, so how do we get in touch with our inner artist? Well, I would recommend, I'll put it up here, work your way up. So work up one dimension at a time. If you're not comfortable, this is a nice way to step things up. Okay, so let's talk about -2 less than or equal to x less than or equal to 2. Well, that's just saying in the x direction, we're going from -2 to +2. So that's pretty simple to understand. Okay, so the outer layer, no problem. Now the middle layer, we're going to use both the first and second one to understand that shape. Okay, so now we're in x and y. So we have x and y. And, okay, well, what can we say? Well, we have some curves. Y equals 0. What does that look like? Looks like this. This is y equals 0. Okay. What about y equals 4 minus x squared? And I realized I didn't draw this quite well enough. What does y equals 4 minus x squared look like? Yeah, it's a parabola. Its peak is at 4, and it goes down. Where does it intersect? Ooh, isn't that convenient? Because x is going from negative 2 to 2. For a value for x, y goes from 0 up to this 4 minus y squared. So our outer layer is this piece of a parabola. All right. Cool. Now, our next step. Trying to incorporate this into the third dimension. Okay. So, are we good with the up through the outer layer and the middle layer? This should feel like what was happening when we did two-dimensional integration. That's because that's what was happening when we were doing two-dimensional integration. So there's a reason it feels that way. Now we go one more layer in. Okay, so let's talk about what these surfaces are. So there's really two surfaces here. One surface is the surface z equals 0. The other surface is z equals 4 minus y. Do we know what z equals 0 looks like in the three-dimensional setting? It's the xy plane. So z equals 0 is like the floor here. So this is the xy plane, z equals 0. What about z equals 4 minus y? What would that look like? It is a plane. Very good. It's not a line. Why is it not a line? Well, because we're in a three-dimensional setting. What is missing from this equation? Z equals 4 minus y. X. So when you see a missing variable, that doesn't mean it's a two-dimensional thing. It just means, you're going to copy the two-dimensional thing back and forth. So think about the two-dimensional picture. If we said z equals 4 minus y, thinking two-dimensionally, well, we're in the yz plane. Let's say we'd intersect here at 4 and 4, because if you put in z equals 4, y equals 0, or you put in y equals 4, z equals 0, they both work. You get a line segment, and now you copy that line segment in the x direction. So it's a tilted plane. Okay, so those are our two surfaces that z is going between. Okay, so now comes the fun part where we put it all together. So we'll leave ourselves some space in case we make some mistakes. All right. So we have x, y, z. And for reference, I'm going to mark what this looks like in our picture. So we are going from negative 2 to positive 2. And here we'll say this is at 4. And we have this parabola. Okay, so this shape is over here. Now, what's happening with z? Well, z is going from 0, which is the xy plane. So this is the floor, and we're going up to our surface. Now, that surface, here's z equals 4, and we're going down. It hits right here. So this is our top surface, z equals 4 minus y. And how are you doing? You hanging in there? I'm sorry, I am going kind of quick. I feel like I'm explaining it well to myself, but I don't know if I'm explaining it well to you. Okay, so what's happening? When I'm looking at this dz term, I'm thinking about going up and down. dz says move in the z direction. So I'm moving parallel to the z-axis. So I want to move from my region that came from my two-dimensional thing, and I'm going to start at the bottom, which is 0, move up until I hit the top, which is the plane 4 minus y. So I'm going to do that at every point. And then I'm going to say what's happened. So what I'm getting is a shape that's doing roughly this. Let me see if I can sketch it one more time. And it can be hard. This is the part when I may have said this in class at some point. If I haven't, I'll say it now. Calc 3 will really push your geometrical understanding. And this is about as hard as it gets. It's trying to understand how all of these are coming together. So -2, +2. Over here we have y equals 4. Then we go straight up. And we're coming down and up. So what we have is we really have 4 bounding surfaces. This back surface, what is this bounding surface? Yeah, so we have the y equals 0 is our back side. Y equals 0. We also have the floor. What's that surface? Z equals 0. Then we have the slanted face, which blends in too well with the bottom. But our slanted face, what is that? That's our z equals 4 minus y. And then our final thing is we have this curve. So this side here, which also comes around and becomes this side over here. What surface is that? Yeah, so it's y equals 4 minus x squared. That's that last side. It's essentially that y equals 4 minus x squared copied up and down. Because we're moving from the parabola straight up until we hit the plane. So that's our shape. That's our sketch. Now, I think on exams, I don't know if we've ever actually graded for sketches. But you need to get some sketches if you're going to hope to do the next part. And you might say, well, what's the next part? The next part, any questions on our shape? Don't worry, we'll see it again in just a few minutes. Is changing the order of integration. So, just when you thought, change the order of integration, that seems too easy in 2 dimensions. Well, let's do it in 3. Okay, so, how do you do it? It's a similar idea as to what was happening before. So, what do? You identify your current bounds. Why do we identify our current bounds? Our bounds are our way to describe the solid. Once we have those bounds, we can use our bounds to draw a picture. Work your way up. we're not going to have crazy expressions. They tend to be very simple. So planes, cylinders, things where we have one variable short. So draw a picture, label your surfaces, and solve for your appropriate variables. And then you work. You can work from the outside in or the inside out, but basically be consistent. Find your new bounds, which is basically find the new way to describe your solid. And there's a note, why change order? It might lead to more or fewer integral terms, is one thing it might happen. Okay, so we have an integral. Negative 2 to 2, integral 0 to 4 minus x squared, integral 0 to 4 minus y, f of x, y, z, dz, dy, dx. It says, hey, change it. We want dx, dy, dz. All right. Well, what do? We identify the current bounds and we draw a picture and label the bounding surfaces. Well, good news. We've already done that. So let's just copy our work. So we can join this problem sort of like halfway through. So minus 2 plus 2. Here's a 4. Here's a 4. And we have our base. It's our parabola. We go and shoop, shoop. Okay. All right. So here's a picture, and then we've marked our surfaces. Our back face was y equals 0. Our bottom was z equals 0. Our slanted top was z equals 4 minus y, which, by the way, is the same as y equals 4 minus z. And then our other pieces was part of the parabola, and that's y equals 4 minus x squared. Now, dx, dy, dz. Ah, the good times. All right, should we work from the outside in, since this says work from the outside in? Now, here's an idea. There says there's a tip here. Look down an axis. You might say, well, what does that mean? Well, what's the last thing we're going to work on? The x. The x is the inner thing. So let's make it, if I'm just focusing on the outer layers, the y and the z, well, if I want to just see the outer layers, it's like I don't want to see x. So what I'll do is I'm going to grab a hold of the x-axis and pull it. So we're turning so that we're going to look straight down. So, if you're looking straight down, then the axis, which is a line, becomes a point. So as we look straight down the x-axis, we only see the y and the z. What shape do you see? We see a triangle. Where do we hit the y-axis in this triangle? Where do we hit the z-axis? 4. And so looking down the z-axis, that's the shape we see. Now, given that, can you tell me about z? Where does z go from? 0 to 4. See, this isn't so bad. How about y? Well, given a value for z, I move back and forth in the y direction, because dy says change y. So 0, that's pretty easy to spot. Now this curve here, this is z equals 4 minus y, or y equals z minus 4. We're doing dy. Which one of these do you want? Yeah, you want the dy says I want y equals. So you want the z minus 4 term. Okay, now we come to our last one, x. We've got to go back into our picture here. Now, for x, we want to be going backwards and forwards in the x direction. So move in the x direction. So you start thinking, okay, what surfaces are we going between in the x direction? Which ones do we hit? Which parts are we hitting if we move back and forth in the x direction? Yeah, we're hitting this parabola here. But we can't have y equals, we need x equals. So what do? Well, this is x squared equals 4 minus y. Or x equals plus or minus the square root of 4 minus y. Well, which is it? Both. Good. Because you have this part where the x is positive, this part where the x is negative. So we're moving between, x goes between minus square root of 4 minus y and positive square root of 4 minus y. Which one goes in the first slot, the bottom slot? Negative. You always go from low value to high value. So negative square root of 4 minus y to positive square root of 4 minus y. All right. And our time is almost up. Oh my gosh. And we still had like 4 problems to go. But let's just throw something up here. Why would we want to change the order of integration? I will say one more problem here. We'll do a multiple choice problem. Here's an integral. Integral 0 to 1, integral 0 to 1, integral 0 to 1, z squared x, e to the xy z, dz dy dx. What would you want to do with this integral? Because currently it says integrate with respect to z. Is this the kind of integral that you'd like to take with respect to z? No. Well, would you like to take it with respect to x? No. So what should you do? We should do it with respect to y first. So that's changing the order of integration. Now in this case, it's very easy because it's a cube. And if you work it out, you'll see that the best order is to change it to dy dx dz, because then you don't have to do any integration by parts. It's just a matter of working through it one layer at a time, and you can get an integral that's easy to compute.